Yeah, so first I want to thank the organizers for putting together this wonderful program. Also apologize that thanks to Lufthansa Airlines, I spent day in Frankfurt Airport rather than here, which would be my first choice. Um, but I'm glad that I'm here, and I'm glad that you guys came for this last talk. So as you can see, I'll try to make it slightly entertaining because it's been a long day, and last talk maybe should entertain a little bit. So if you Google black swans, then one of the first references in Google actually will come to this black swan theory. And this theory or idea got very popularized recently by Nassim Taleb. So he's a Lebanese economist. And the story goes all the way back to actual question about black swans that people believe did not exist until fairly recently in history. So if you can read this small font or Google on your laptops, you'll see that essentially up to 1700, there was a prevalent belief that all swans are white. And then black swan was discovered in Australia. I'm not sure if this is a picture of the first one or probably not. But now we know that, yes, of course, there are black swans. And Nassim Taleb, among other people, popularized this idea, especially in financial markets, where you quantify outliers, data points that don't belong to most expected or natural distribution. So they're called black swans. So this basically forces people to think about what's my distribution, what I expected, and what are outliers or least or less expected events. So this is one quantifier. Another quantifier is that, and that's maybe more important, the second aspect is that this black swan, once it occurs, this rare event, its effect is very dramatic. It changes your perspective. For instance, until roughly 1700s, there was one belief or dogma that all swans are white, and that qualitatively changes after the event occurs. It's no longer true. So that's, keep it in mind. So you're probably wondering by now, what does it have to do with resurgence, and am I in the right place? I may still be sleepy, so I may not have arrived at the right conference. I assure you, yes, there is. It has a lot to do with resurgent analysis. We'll get to this in a minute. And in this talk, I'll try to cover several results, which are based on some recent work. Looking back at this last year, I realized that, in fact, pretty much all of my papers happen to be in resurgent analysis and various aspects of a connection to either mathematical physics or various topics in mathematics. I guess it indicates that I love resurgence, but I didn't realize myself that that's the case because I thought of them as quite different. And from each project, I'll describe a very small part of it. Many co-authors or some of them are even in the audience, so I encourage you to talk to them to probe for more information or other things. And coming back to black swans and other things, we, or people who superficially or somewhat familiar with resurgent analysis usually think of it as a very technical tool that's very good at doing some delicate calculations, extracting exponentially suppressed terms or making sense of, it's basically a computational device, a strong computational device. And this will be represented in this talk. I'll show you a couple of applications where the strength pays off. But I also want to emphasize that it actually helps to answer simple qualitative questions. And this, again, not maybe too surprising to practitioners, but I just want to add to the list of potential applications one more. And this part will be based on recent work with Pavel Putrov, and I'll touch on two other papers from earlier in the past year that Ovidiu, Gerald, my former student Angus Gruen, and current student Mune Jagiro. So I don't need in this audience to say more about resurgence. It basically, it gets the strength from projecting the problem from potentially high dimensional space, where it could be space of fields, to just complex Borel plane. And the whole action happens in complex Borel plane. That's actually way to make sense of very complicated problems most of the time. That's where Resurgence actually derives its strength compared to working directly in much bigger configurations. So I'll assume that. I'll also use a notation that critical points will be called alpha. So these are saddle points from, say, mathematical physics perspective or singularities on a Borel plane. I'll call them by alpha. And one qualitative question we can ask, and that's what I want to discuss, is that suppose you're given perturbative quantum field theory, something that we learn in textbooks defined by such integral. Here, I presented in a form which looks like it's a gauge theory. It may be your favorite gauge theory, say Young-Mills or something like that. It could be a theory of scalar fields or spinors. And thanks to Mr. Feynman, we know how to set up the problem so that we can do concrete computations perturbatively in each order of h bar or other coupling constants if they're present. But one question which we still don't know how to answer in general is, what is non-perturbative completion? In fact, it's a highly non-trivial question, which perturbative QFTs have non-perturbative completion? This is far from being answered. We don't even have a guess. We don't have a conjecture. We simply don't know. And that's a very concrete question. And what we did learn in the past 60 years of existence of quantum field theory is that sometimes when we can make sense of non-perturbative completion, these are still rare cases, it means that theory has to be enlarged to something bigger. For example, half the time, what happens is that you take perturbative QFT, you try to make sense of it non-perturbatively, and it turns out that that non-perturbative completion is a theory of even different dimension, could be high dimension. Sometimes it's the whole string theory that is non-perturbative completion of something perturbative that looks like quantum field theory. So the question is, how much bigger this theory should be? And one natural question is, if you're working with a perturbative QFT, you can ask, does it have a chance to be, to provide non-perturbative completion within its own framework? Namely, can I hope to not introduce any additional fields? Can it just be, instead of contained here, really equal, that non-perturbative equals what we already have in the perturbative lab? So that's a good question. It's not clear how to answer this a priori, especially if I pose it as a such broad philosophical general question about QFT. But this is where Resurgence can provide some useful clues, because we can probe this question. We can devise the following criterion, which in practice I think is pretty good. We can see, ask the question, do we see only the saddles of the original QFT on the Borel plane once we start doing resurgent analysis in this expansion and H bar? So if we see some points on the Borel plane which are not classical saddles of this original theory, then we can be pretty sure that its non-perturbative physics does require some completion, and this other theory, non-perturbative completion, is strictly larger than QFT. Of course, I should probably make a disclaimer about renormal-ons, which we still also don't quite understand. There is a lot of progress, but there are also lots of questions. So modulo those questions, this could be a useful test of what non-perturbative physics looks like. Namely, if you see only saddles of the original theory on a Borel plane, then it's a good indication that, yes, probably it could be its own, or non-perturbative completion could be formulated within its own original framework. But if you start seeing something that does not belong to the list of classical saddles of the original path integral, then you would probably expect that something interesting should happen. So this could be a good test and answer to this qualitative question. And this is precisely where this question about black swan appears, because if you work with simple examples, you may only encounter saddles of the original QFT. But if you go to more interesting situations or explore a little bit more, maybe go all the way to Australia, then you find instances where you see singularities on a Borel plane which do not seem to correspond to saddles of the original QFT, perturbative QFT. And this is what I'm going to call black swans in this context. So something that's expected is sort of boring, but something that's not expected is exactly this rare event whose impact on our understanding will be quite dramatic. It will tell us that perturbative QFT or framework of the original theory is not enough. Is this? Yeah. Any questions at this point? Is everybody happy? That's as a candidate for non-perturbative physics, if I understand your suggestion correctly, right? Or it may or may not. Exactly, yeah. It may or may not be well defined. Yeah, so it depends on what we have. So unfortunately, this works sometimes, but it's not all. Yeah. Well, like I said, this is criterion. I'm not saying that's always going to work. And I already made a couple of disclaimers. For example, sometimes there are these additional points. So it goes both ways, yeah. So even if they are, we have to rethink a little bit about the nature of it. But yeah, that's another good question. And there are certainly examples I can expand the list where it doesn't indicate, it looks like it's passing the test. But so that's why it's just a criterion. I wouldn't say it's one-to-one. Very good. So, right, I'll give you an example where it does indicate something interesting and where it behaves the way it's, where it can be productive. So take your favorite gauge theory, again, the way I'm writing it here, and make something quite ridiculous. Usually with gauge theories, we believe that there is some way to make sense of it. Sometimes, again, we're pushed to work with string theory as a completion, but we can try to make something quite strange, namely make the gauge field complex. So that will immediately break all the laws of traffic rules, because theory will typically become non-unitary, things will go bad. And one way to see it is that the space of fields now will become very non-compact, because if I think about this phi as scalar paired with my gauge connection, that's imaginary direction, then in those directions, the field space is going to be very, very non-compact. So I'm already asking for trouble. That's intentional. So this modification was to take something that had a chance to be, I'll say, normal, or perhaps completed within its own universe. And now I'm definitely asking for trouble because I have this non-compact configuration space. So in many problems in mathematics that involve geometry, for example, in symplectic geometry, in Gromov-Witten theory, where people study curve count, or in various other problems where moduli spaces appear, typically the issues arise when these moduli spaces are non-compact. So one has to say what happens and regularize or define the problem. So this non-compactness is going to hunt us one way or the other. And again, typically one has to find a way to regularize it, or in practice, compactify such non-compact either configuration spaces or moduli spaces. So this can be done by adding something at infinity. That's where this regularization or making sense of theory comes in. And now that's a source from our standpoint where additional saddle points can appear. So I intentionally draw this saddle point, which is new, and add it upon regularizing the theory in black, and I'll call it a black swan. So that's exactly such a candidate. So we can ask, in this context, what does Borel plane look like? And in such situation, it's perhaps not too surprising that there should be black swans if, again, my problem is already calling for this. In fact, the scenario I just outlined is realized in a concrete example. So for about 30 years, people pushed the program of understanding complex Chern-Simons theory, looking for its non-perturbative completion, which recently more or less converged, and now there is a very good definition, and it's easy to work, and so on. So here I'm basically outlining its precursors. So this completion involves, so it's Chern-Simons theory where you do exactly what I said. You replace gauge connection by its complexification. And people realize that it's hard to make sense of it staying within the same framework of Chern-Simons theory. You're basically forced to push this to string theory, and the relevant configuration involves 5 branes, which are 6-dimensional, not 3-dimensional anymore, partly wrapped on 3 manifold on which you want to define your Chern-Simons theory, and 3 other dimensions of 5-brane world volume are used in a certain way where geometry is unique. It's basically S1 cross a disk, or put differently, a solid torus, such that on the boundary of this solid torus, you have complex structure tau on the elliptic curve that's related to Q in the usual way. So that's where quantum parameter of Chern-Simons originates, and this string theory setup, which again has very, very long history. And you can put here any general 3 manifold and so on. And because there are 2 3-dimensional spaces involved, a while back, this was called 3D correspondence, which is a relation between complex Chern-Simons on a 3 manifold, which is now non-perturbatively completed. So that this side, and on the other side, you have some 3-dimensional n equals 2 theory, which looks like supersymmetric topological, but 3D correspondence relate them together. So in this context, that's precisely kind of this, some violent operation on normal theory. I took Chern-Simons theory with compact gauge group, usual gauge field. I added plus I a phi, which is imaginary part. And that's exactly where all this suddenly complexity happens. In order to make sense of it, we learned, starting with works of Gukov and some of his co-authors and other people, that the right thing is this system. So it's not the same type of theory anymore. So here, already from the start, before we do any calculations, just from these lessons, we would actually expect that there should be some kind of black swans, which are new saddles that are not associated to flat connections, in this case, complex flat connections of the original Chern-Simons. So that's concrete illustration of it. I want to pause for a second to make a couple of sort of advertisement for these early works, which some of us who worked on the subject 20 years ago knew well, and they were great inspiration, but I think now they're mostly forgotten. And there are many reasons to actually use them or even refer back, because already back then they did some preliminary calculations of this non-perturbative complex Chern-Simons on various families of 3-dimensional manifolds, closed 3 manifolds. And they found that the answer is nicely expressed in terms of Q series with integer coefficients, such that these integer coefficients are counting some BPS degeneracies. And I'll come back to this in a later part of the talk. These people actually also asked questions about modularity, which I know is the subject of interest here as well, because I mentioned that this geometry contains a 2-dimensional torus, and the question about origin of the modular SL2Z group here is very manifest, just the symmetry of the system. In fact, this picture is very useful to understand whether in some cases the symmetry should be SL2Z, or it should be some congruent subgroup such as gamma 02, gamma 04. So this happens sometimes. And this clearly has advantage over various approaches where sometimes SL2Z comes just out of the blue, and one doesn't really know when to use SL2Z versus congruent subgroup. So this was a very useful step, and these people actually did ask modularity questions as well. So one last thing I want to emphasize about the slide is that something else happens, and this will also shift our focus, and this seems to be quite general phenomenon, that we start perturbative expansion in what I call perturbative QFT in terms of parameter h bar, but once the theory is non-perturbatively completed, the natural expansion parameter is exponential of h bar. So that's what this parameter q is. And this happens quite generally, and again, by now for very good, well understood reasons. So later in the talk, I'll use both q and h bar. So I want you to remember this relation, which again goes back to mid-90s. Yeah, yeah. This six manifold is not Calabi-Yau, but this setup, once you embed it in string theory or M theory to be more precise, because these are fibranes, for this part to be topological, it has to be embedded as a Lagrangian submanifold in cotangent bundle of M3. So that is Calabi-Yau. So the ambient space for this, where this fibrane lives, is contains a Calabi-Yau. No, it doesn't. So the full 11-dimensional spacetime is something like R5 cross Calabi-Yau. That seems to be of interest here. So this is complex threefold. Real threefold, three manifold is embedded as a real slice. Lagrangian is a very good condition for it, of course. And roughly speaking, we have R3, or I should modify this in some ways. So that's the geometry. It does contain Calabi-Yau, but not exactly, not this space. Okay. So by now, if I ask you a question, would you expect that this theory should have saddles which are not complex flat connections? You would probably say yes, because that's a perfect example where we took something, we tried to make sense of it non-perturbatively, and mathematically it means that it behaves well under cutting and gluing and various other operations. And you would expect that, yes, there should be saddles which are not original saddles of Chern-Simons theory. And this is actually a nice story, because when people were working on this, I don't know, about 20, 15 years ago, there was some vague expectation. I hope nobody made an explicit conjecture that saddles should only be complex flat connections. But now, of course, as the story progressed, and even by then, there was clear evidence that non-perturbative completion is just bigger. So by now, we see that there are indeed saddles in this particular theory, in this particular setup, which are simply not complex flat connections on the three manifold. So that's a very good experimental evidence, and this black swans took some time to discover. So in particular, in this paper with Pavel, we exhibit some concrete examples, but also propose many new ones which should be looked at more closely. So from now on, I'll switch gears a little bit. That's interesting story about this complex Chern-Simons and how it evolved. I'll shift my focus to the variable Q. So my story started with H bar and perturbative expansion and turning it into Borel plane. And in fact, I'll broaden my scope to other subjects. So the next part, which will be based on joint work with Gerald, Ovidiu, and Angus Grewing, applies actually to many setups, and that's an exciting part. And in particular, it does apply to this non-perturbative complex Chern-Simons if you wish, but it can be applied to other things. Yeah, sure. I think a lot more effort should be put into understanding them both physically and mathematically. The way I think about it, you can ask Pavel if he agrees, is that they come from precisely this compactification divisor sort of perspective. But since they're, again, kind of new, and even though they were expected for 30 years, there are still black swans in the sense that more effort should be put into interpreting them and understanding. So I would prefer to answer this question by encouraging people to do more work on it. So there are now clear candidates. We even outlined like what they should be, where to look, and so on. In some cases, we make them very explicit, but I believe a lot more should and can be done. Pavel may be unhappy that I'm giving slightly incomplete answer to this question, but this is intentional. So if it's okay, I'll move to the Q, and we'll talk about Q series in general. So many people here love Q series for all kinds of reasons. Either you love Resurgence where Q series appears, or if you work with modularity of any kind, Q series is usually how we do practical things, concrete things. And this actually applies to many other branches, for example, vertex operator algebras. So that will make very close contact with Joanna's talk this morning, quantum curves, quantum topology, quantum groups, and so on. Actually, many of them will appear. So this part will be slightly more technical. I promised that first part was like appetizer. It was fun. This one will be a little bit more serious. I'll try to explain certain phenomenon or certain aspect of it. And in whatever application you're thinking of, keep in mind this slide or this quote from Sidney Coleman, who I respect dearly. So I think it applies perfectly to our context that all this Q series will simply be encoding in whatever we're going to look at the spectrum of a system. Very much like a spectrum of harmonic oscillator, you can package in a Q series, which of course is just a geometric series. You can write it very simply as a rational function. Everything else, no matter how complicated, no matter how complex Q series I'm going to show you, think about it as expansion in energy or some generalized notion of energy. It's actually literally true pretty much in every system. So when we usually use categories and so on, we overcomplicate things. But that's what it's going to be in every concrete context. So then I want to draw your attention to the following phenomenon, but it was discussed here before. So we call it going to the other side. So I think the term was proposed by Miranda Cheng when we were working on this paper 3D modularity back in old days. And my goal will be to describe some perspective on this phenomenon, complementing what Joanna already said. And a certain problem whose resolution I did not expect to find until recently. In fact, we were working on a very long project with Gerald, Davidio, and Angus, and sort of solution to this question that I'll try to explain came as a surprise to me. So thanks to their bravery and courage. So this phenomenon, it's a duality. It's a bijection between two sides, and two sides, surprisingly, are quite asymmetric. So there'll be many puzzles or questions about this duality or bijection. One of them is why is there such an asymmetry? So again, no matter which walk of life you're gonna choose your applications from, I'll give you several. You can work with vertex algebras, with topology, with physics. There's always this asymmetry, and it plays very different roles. So I'll try to shed light on this, and we'll talk about it. So in fact, the list of topics could be long. My time is finite, and I'm told that I can go indefinitely and have 2 hours for this talk. I'll try not to do it, so I'll limit my applications to quantum algebra, low-dimensional topology, and physics. In fact, physics not very far from what we're already seeing in the first part, so that we don't have to jump between two different physical systems. So think about some Q series, such as, for instance, this one. Many Q series that we'll consider, they have some enumerative meaning. So they have meaning of counting something. Physicists usually refer to them as counting BPS states. In mathematics, we formulate the problem as counting either Donaldson-Thomas invariants or dimensions of spectrum and some DOA module and so on. Whatever it is, again, pick your favorite application, whatever your favorite area is. It could be character of CFT or maybe three-manifold invariant. Imagine that the answer looks something like this. So first of all, you can ask, can I write a closed form expression for it? And in this case, for instance, this is closed form expression. So Then we'll try to do the following interesting operation. We'll try to ask in this Q series, can I take Q and replace it by Q inverse? Okay, so let me be naive. And in this particular example, if I stare at the first line, I don't know what to do because it will turn Q series into series and Q inverse. And I want to still rewrite the answer as a Q series. So in other words, I want to take this original object and extend it across natural boundary, which in classical textbooks would be no. I mean, the answer, I mean, that's why it's called natural boundary. It should not be able to go through to the other side. Okay? But let me be naive and like a high school kid, I have an expression which is sum of these terms. This is Q-Poheimer, so this is actually every term is a rational function Q. So what I can do in every term, replace Q by Q inverse, and then multiply by some big enough power of Q so that everything looks again in terms of Q rather than Q inverse. Okay. This is something we can do on the back of the envelope when we're riding the bus or when we're walking from our hotel to this institute. So it's very quick calculation. This is how result looks like. And you already see, for instance, if I really do it in this concrete example, that there is some asymmetry. So this is rather sparse. And this will actually, if I continue the expansion, it will be much more dense in terms of its coefficient. So that's already some asymmetry. And this is precisely the symmetry that we want to study. But of course, what I just did is terribly illegal because, first of all, I use the fact that there is such a nice Q hypergeometric form for this function, which may not exist, or if it does, it may be non-unique. In fact, in the paper with Gerald and the video, we give many examples where it's not unique, and we show that if you do it to one, you get one answer. If you apply it, I mean, this naive trick to another, you get something ridiculous which doesn't match with what's expected. But so this seems like nonsense that I'm wasting your time, but something interesting happened in the past 10 years. This question naturally appeared in different areas of mathematics and also physics. And what's interesting is that when there was some very esoteric, complicated way to expect what the dual should be, I denote the dual by check, it actually agreed across different fields. So people in vertex algebra, as I'll explain to you, had a version of this question. They produce one version of f-check, and people in topology produce another version. And curiously, this illegal operation actually agreed. So it suggested that the dual should make sense. And natural question is, okay, how to define it? So yeah, I should also mention that back in the day when we were working on this 5 years ago, by this point, I learned that there is a way to do it using Rademacher sums, slightly more systematically. But this is fairly complicated machinery. And I mean, it works. I don't want to say anything negative about it. But still, my take on it was I would love to understand more conceptually the role of this operation. So what is it? And have something slightly more tractable than Rademacher sums. So if you love Rademacher sums, you may tune off for the rest of this talk. If you, like me, if you want to have alternative perspectives, then that's what I'll explain. So then, but what do I mean by understanding? By understanding, I mean, I want to have an answer when this operation, this illegal looking operation is actually something I'm allowed to do and have a concrete tool how to use it. For instance, in one simple class of functions called false theta functions are labeled by two integers, p, which plays the role of this level, and a, which runs roughly from 0 to 2p, and plays the role of this characteristic. So this is a class of Q series, and one of the examples I showed you on the previous slide is precisely from this family. It's some linear combination. In fact, it's this one. So then natural question is, can I apply this duality operation, this check, to every member in this family labeled by P and A? This is actually a very concrete question, since motion of this going to the other side already appeared back, I don't know, 6, 7 years ago. I went around and many of my collaborators did and asked every known mathematician, what should we expect? Is there something that we can do? Everybody and especially for this whole family, like, is there a dual for every single psi tilde? Yeah, so that's the question that I was asking. And I assure you that 99% of people said no, that's too much to hope for. This whole operation looks so ridiculous. How can you expect this for whole family if we haven't discovered it already? So it just should not exist. And 1% of people said we don't know. There was no ever positive answer. So again, think about black swans. And in this recent work with Gerald, Avidio, and Angus, we actually say that the answer is yes, and we propose concrete mechanism or set mechanisms how to find. So in the rest of the talk, I'll try to shed light on this phenomenon. And as the first step, I want to point out that in various areas, for example, in topology, so if we talk about this Q series associated to non-perturbative complex transhymens, this is also known as TQ of T associated to quantum groups at generic Q. What you see sometimes are answers which are linear combinations of these false thetas. You don't really see answers which are false thetas directly, single psi tilde, but you see various combinations. And that field has its own method. So here, for instance, I just advertised something that was proposed by Sang-Yun Park, which says that if this is your original function, then the dual should look like this. I don't see forest for the trees. I don't you expect to see any forest for the trees in this case. I just want to emphasize that there are already candidates. So if we develop some machinery, we have lots of things to compare to. Because if I propose that there is an answer for single psi tilde, and my machinery is going to be linear, then I should take superposition and just compare it to what was produced. Of course, it checks out. Otherwise, I wouldn't be giving this talk. All right. So before we do something sophisticated, let's try simple examples. In fact, I like the question about QED, so we'll do something very similar where question almost disappears, but not quite. So first we can take Sidney Coleman's harmonic oscillator and just see what happens there. So again, it's in this case, there is no series, there is no regularization to worry about. This is actually where the interesting part of the story is. The fact that we have a series, we need to regularize something. Here is just a rational function of Q. So we replace Q by Q inverse, we go to the other side, and we see that it's actually symmetric. And the only thing is we pick up the minus sign. That's kind of a delicate thing. So this already rules out some speculations, which some people expressed about 5 years ago when this question was posed. They said, oh, if you're talking about the spectrum, probably it's bosonization, fermionization. You just replace bosonic by fermionic. No, that's not what happens, because if it's bosonization, fermionization, they should migrate to the numerator. And you see, it doesn't happen. But we do pick up a minus sign, which is kind of like something fermionic is present, or maybe derived if you like this kind of. We can try to do something else. And for instance, this is spectrum of a simplest quantum mechanical system. We can ask, what is the spectrum of simplest two-dimensional CFT, for instance, chiral boson? Take a character, which would be one over the Dedekind eta function. And here we can try to play the same trick. We can replace Q by Q inverse in this infinite product presentation. So that's what would happen. Then we try to multiply everything by positive powers of Q so that everything is positive. So here we'll get, of course, the same answer, again, up to potentially minus sign. But in the numerator, we'll get Q to the power 1 plus 2 plus 3 plus 4 and so on. And we all know what it is. It's by zeta function regularization. It's minus 1/12, which perfectly conspires with this 1/24 to give us back 1 over eta. So we see that both in quantum mechanical and one-dimensional system or 1 plus 1 dimensional system, this operation on a spectrum seems to return the spectrum. So that's good. That's at least nothing mysterious happens, but this of course is fairly rare as far as I know. So now most of the time I want to spend explaining why this question matters. And I already mentioned that people in many different fields encounter this question, and I'll mostly focus on some math and some physics instances of this question. I'm going to completely omit number theory, which in fact was touched by Ioana in her talk, so this is again very complementary. But in representation theory of infinite dimensional algebras, this question already has, I would say, 30+ year history, and goes back to Kazhdan Lustig, who established what we now call correspondence, and by their name, between quantum group representation theory and vertex algebra representation. So there, they managed to formulate various statements, which some they proved directly, some had to wait until further work contributed. But they saw that the vertex algebra, or if you don't like vertex algebra, think about two-dimensional CFT, behaves very differently at positive and negative level. So if, yeah. And in their notation, negative level was easy, but positive level was extremely hard. In fact, even up to present day, it remains one of the big challenges to formulate this conjecture to understand what should be the vertex algebra and its character, which is related to quantum group at a positive level. When Q is a root of unity, and depending on whether that root of unity is negative or positive on a unit circle, you get two very, very different stories. Again, there is this asymmetry. And moreover, even up to present day, from just pure representation theory, there is no easy way to say how to go from one character to another character. It's expected that representation theory here agree, namely we have same modular behavior of this whole package, but how to replace one character, which in the negative level case for this logarithmic VOAs is exactly this false theta function or some linear combinations thereof that I showed you. It's completely unclear just from VOA perspective, what should be the other side. And there are various formulations of what this VOA should be. They involve very esoteric things like semi-infinite cohomologies of Frank-Grossman, many other things, but they're not explicit enough so you can actually compute character. So you still don't have this answer. So yeah, therefore, my questions would be here. First of all, how, given some, for example, logarithmic VOAs whose characters are, for instance, this false theta functions I showed before, what is the dual object? This is actually still unknown. But what I can answer for you, thanks to our joint work with Joel, David, and Angus, is what happens at the level of characters. So that's very helpful to VOA people because it tells us the structure of the spectrum, namely what happens to the modules of this VOA on the other side. And hopefully one can reconstruct the vertex algebra as well. So in topology, a similar phenomenon happens. And as what I'll try to illustrate, I promise this part is a little heavier, but I want to emphasize that it's actually deep. So in each case, this question is not very superficial. It touches on something very, very deep in that given field. So in this case, it's Kazhdan-Lusztig correspondence for infinite dimensional algebras, but in low dimensional topology, it's precisely the kind of questions which relate to probing smooth structures on four manifolds. To topologists, most interesting invariants of four manifolds should be asymmetric under orientation reversal. So if you take a manifold and you replace it by orientation reversal, you should expect that your invariant behaves in a highly non-trivial way. So actually, this asymmetry is a good thing if you are four manifold topologist, for example. So if you think about, say, Vafa-Witten invariant of four manifolds, which is already a Q-series, one interesting question is how to relate Vafa-Witten partition function for manifold M4 and its opposite orientation cousin. So they're not going to be the same. They're very asymmetric, and that's actually good. So the question is how they relate. So this question actually has many incarnations, and what I showed you before is this idea of 3D correspondence that takes some six-dimensional CFT, produces three-dimensional conformal field theory that depends on M3, and we can study various quantities here, which will be, say, Q-series invariants of three manifolds, or we can follow this route and construct two-dimensional CFT, which depends on a four manifold. And here again, one can take various objects and ask how they behave under orientation reversal. So this is a very important question. Again, I emphasize question is easy to state, but its consequences are very important for existence of smooth structures on for example, four manifold. So from the viewpoint of 3D correspondence, the following is quite natural thing. You construct four manifolds usually by gluing pieces along some three-dimensional boundaries. So that's not surprising. There is no other way to do it. But if you put this through the machinery of 3D correspondence, here you compactify on a three-manifold. So you get something which looks like theory T of M3 on an interval, which is bounded on both sides, where this three-manifold gets kept off by four manifolds. I mean, to derive this picture or this translation, all I'm following is that total dimension should be 6. So when I compactify it on something three-dimensional, I get something three-dimensional, because 6 minus 3 is 3. Here, 6 minus 4 is 2, so I get some two-dimensional boundary simply from this naive count. So you get basically this coupled systems of 2D, 3D systems. And it's easy to work out that the boundary condition here is of the type where you get 0, 2 supersymmetry, very much like in heterotic string. Anyway, you get this kind of coupled systems, very interesting. You have these boundary conditions. My wave is bouncing back and forth. So that would correspond to some particular choice. And this is relevant, again, to a number of questions. First of all, four manifold invariance, if I want to think about this as cutting and gluing of my four manifold and constructing this theory T of M4. It's also related to this, what people sometimes call GPPV invariance. So that's non-perturbative completion of complex consignments, or this TQ of T associated to quantum groups at generic Q. So that's the Q series that you get following the path of Gopal-Kumar-Vafa and many others. In addition, actually, even in this context, from this coupled system, you can also recover the characters of log VOAs in their mod. So it's arena for many things that we have already seen so far. So natural question then is, what happens if I try to do orientation reversal in this system? So again, there are many applications, but I take this coupled physical systems. Now I'm talking about physics. 2D, 3D coupled system, and do parity operation. So say orientation reversal on M3 if this is in the context of 3D, 3D correspondence. Well, then it's easy to see that the operation which will compensate it is parity operation on this part of 3D, 3D correspondence as well. So that sounds very simple. But remember that I have a boundary condition. And the reason something non-trivial happens in this partition function, which counts like its elliptic genus for this 2D system, but also coupled to the 3D bulk, is because my boundary is not asymmetric under parity. So left and right are very, very different. So that's indicated by the fact that I have 0 on the left and 2 on the right. So I cannot just say that, oh, I have a candidate that takes my boundary condition, whatever it is, and replaces by a dual. It's a non-trivial duality. That's where the interesting part of the story is hiding. So in other words, this operation, again, think about these proposals in early days. It's not like Bosonization at all. It's more like, I mean, it could be viewed as Bosonization for minimization, but it's more like supersymmetrization and desupersymmetrization, because you try to take the left sector and put it on the right, but in order to do that, you have to supersymmetrize it first. So that's what really happens. And we have no idea how to answer this question at a physical level. It would be nice to understand this duality physically. So now I'm speaking to physicists in the audience. This is an open problem. I have no idea how to do it, but this machinery tells us that there should be a definition of this operation. Just like it seems like there is a duality between negative level and positive level for Kazhdan-Lustig correspondence, and just like there is a duality between manifolds with one orientation and the other. So in all of these instances, there is something to be asked, and here I'll go quickly through the proposal. It's of course based on Resurgence, but maybe before I do that, are there any questions about this part? So we got through the most technical part, I would say. This was like review of question why. Why is this interesting? Why is it useful to other people, not just us? Yeah, so to such system, you can assign Q series, which is basically elliptic genus of this combined 2D, 3D system, or it's called half index sometimes, or it goes by other names. I mean, yeah, something like 2D version or 3D version of Nekrasov partition. But you have Q series to each such system. It will be topological on three manifold, from the three manifold point of view, but from this point of view, it's not topological. It's basically taking, so there are two supercharges preserved by this combined system. These are exactly the 2 of 2D02, and you can take Q cohomology of one of them and then take the trace. So that it's like elliptic genus definition. And that counts, again, BPS state or supersymmetric state. So you get naturally Q series out. Yeah, so I included in the past the TMF in gray because this is further extension. This would happen if you study 0-1 version of this story. So, but questions still exist because 0 and 1 are not equal. So there is still asymmetry between left and right. And the question still exists, what is the TMF class for M4 and M4 bar? So they're expected to be different. And just like TMF is refinement of elliptic genera, same question would actually exist. Exactly. Or, I mean, I would, yeah, so first one can ask question about elliptic genus as a Q series, but then luckily in this context, one can even refine it to the TMF class, which will contain torsion, not captured by elliptic genus. Well, that's precisely, I mean, what you would expect from this, because reversing orientation is literally like trying to replace Q by Q inverse, but still keep it as a Q. So in TMF, this would be something completely unexplored. So it basically means that there is highly non-trivial involution now on TMF classes, which implements this operation. So that's even better than trying to do it numerically with actually function of Q series. It's a very good question, completely unexplored. So in fact, thanks to you, I think I should put, sometimes I mention this questions or problems for work. So this is a great question. There are like buffer-Witten invariants in a sense that, and I don't know the answer to this question. So some of our collaborators, like Fagan, they expect that they're related in a way that I don't know. Because if you have a 3-manifold, I don't see a super canonical way to construct 4-manifold out of it. Maybe like M3 crosses 1, but you can easily check that no, I mean, it's not related to buffer-Witten of that. And it's not expected from this physical setup because remember, to build 3-manifold invariant, I had in 6 dimensions, it was S1 cross D2 cross M3, but even though I had S1, it was actually mixing with D2 with the disk. So yeah, I don't see direct relation. But again, people expect something like that. And what one can say is that they behave similarly. So buffer-Witten invariants turn out to be characters of this like VOA from 4. Likewise, this Q series that we get for 3 manifolds, they're characters of log VOAs and so on. So there is a close parallel between those stories. But I don't know really. Okay. Any other questions about this part? Right. So this I'll say very briefly, and luckily we have Gerald and Ovidio as my lifelines. So like I said, we were actually doing something else. We were studying resurgence for various surgeries on twist knots, and we were thinking about title of the paper being completely different, like resurgence for surgeries. This was, but then in the process, and I was asking them this question, of course, all along. I hope they're not offended. At early stages, the paper took maybe a couple of years to complete. They said, no, Sergei, this is too far. Let's just do what's manageable, okay? And luckily, occasionally I kept asking questions and we were revisiting it and so on. So at some point came sort of breakthrough. This is typical dynamics of a project. And once the door is open, this breakthrough kind of multiplied. So by now, 2 to the there is not only one method, but several methods, and they're converging. And again, technology is evolving very fast. So I'm actually very excited about this part. So I'm very glad to share it. So of course, what you do is you do resurgent analysis. So you take your Q in the same relation with H bar as we had before, and go to this very symmetric point. In fact, you can actually do this at any point on the unit circle. That's perfectly fine. But this is slightly more canonical, Q equals 1, so we'll do it there. So at the level of H bar, the operation that I'm asking for is very simple. So the operation for the perturbative series is simply replacing the perturbative expansion coefficients in H bar by their minuses when this power of H bar is odd. That's all there is. And I basically ask, if you can resum this, can you resum the other guy with some minus sign sprinkled every other step? So, sounds very easy, but it's precisely the implementation which is hard. So again, I'm not going to describe this part. My goal was to describe why we do this. So how we do it or what we do it, I'll go through very quickly. But I want to illustrate that it's a very concrete thing, and particularly we can get something new out of it. For instance, for this false theta functions, which I stressed in the beginning, could be very basic test. It's not the only thing that we care about, but since they appear in log VOA characters, they appear in many other fields, it's a good thing. And again, it's interesting to go contrary to what was expected 5 years ago. We were told that, no, guys, you have no hope to construct duals for every value of P and A. So with this method now, it seems that we perfectly can, and there is nothing wrong. Good thing about this class of functions, and if you're gonna try to apply these methods to something you care about, such as Buffer-Witten, for example, partition function of some 4 manifold, you can ask, what is the dual for M4 bar? And try to reconstruct it kind of this way. What helps is if you can get Borel transform in a closed form. So luckily for these false theta functions, Borel transform in terms of variable psi is known. It's very simple. In fact, it's something that people used for many other purposes many times. So having closed form is helpful. And based on that, you can actually start reconstructing coefficients. Like I say, there are several methods, and these slides are borrowed from a talk I gave many months ago by now. And this was one of the first where coefficients of the dual object were constructed one at a time. So here I have my original psi tilde, for example, for P equals 5 and A equals 1. And our goal was to reconstruct the Q terms in the Q expansion of the dual object. And it was one by one. So it was a series of very successive systematic approximations that we did using this Borel transform, where you would examine what these functions, which I'm not going to describe, do. They're supposed to asymptote integer value and then drop down where your approximation breaks down. So you would read off integer values from where they have this kind of peak or maximum where they're tending. For instance, here the blue and the green have 1, and these are the terms 1 and 1 here. I don't remember which one is which. There is caption in the paper, you can look it up. Then something else tends, for example, this red is definitely 0, so that's probably this guy, and so on. So you have a very concrete device to work out what each successive step is. By now, Gerald and Ovidio and Gerald's student developed even more robust and efficient machinery, which completely replaces this, but this works. And in this particular case, very nice paper by Gordon and McIntosh already had the answer. So in some sense, this could be example, which is either disappointing because it's nothing new, but it's a good thing that there is a test. And of course, their perspective was completely different. So we just used resurgence analysis, and that was the goal, to make it a useful tool for people so that you can apply it to any spectrum, which can be phrased as a Q-series the way you want. But then we went to P equals 7, and luckily this particular guy for P equals 7 and A equals 1 was in none of the papers. So this is exactly the interesting case where everybody would tell us we shouldn't expect any dual in the first place. But from the point of view of this method, it's just, well, slightly more complicated because P is larger, but then you still recover the answer, and that's it. So that's the benefit of it. And I should mention that we even outline what it means to have this as an answer, because remember in the beginning I mentioned that there is clearly something special going on. So it's crying out for uniqueness statement. So we try to outline how that would also go. All right, so I think I'm probably out of time. Yes, so I want to finish with one last slide, which is yet something else, and is also closely related to this particular three-manifold invariance. So this is three-manifold story, where in the paper about a year ago with Mrunmei Jagadel, we asked the following simple question. So it's already being discussed, in particular in Joanna's talk, that this three-manifold invariance, this, again, non-perturbative complex Chern-Simons, is surprisingly character of some logarithmic VOA. So then if you're a CFT person or VOA person, the first question you ask about VOA is, what is the central chart? That's a very basic question, namely how fast the coefficients grow. If your theory is not logarithmic, then Cardy taught us that using modularity, you can quickly give a formula for this, for the effective central charge using modular type behavior. But we're in a more general situation. And that's precisely what we analyzed a year ago in this paper with the Mrunmei. And what we concluded is that, well, not surprisingly, because again, of many developments over the past 30 years, it's dominated by one of the saddles on a Borel plane. But then again, when this was even a year ago until this work, people were speculating that the question is which saddle it is, because if you have a manifold, three-manifold, there could be lots of complex flat connections, even if these are not black swans. So then people were speculating, oh, it's probably the one with smallest Chern-Simons value or with the largest. And they were all over the map. It's neither one. It's neither smallest nor largest. It's actually the one where the first non-trivial Stokes coefficient is non-zero. So we give an answer in terms of Stokes data for this question. But what I'm here proposing as a research problem is to give intrinsic definition in terms of something else, in terms of invariance of three manifolds, or maybe this 3D n equals 2 theory, an answer which does not involve Stokes coefficients. That would be actually very, very useful. Namely, how to pick this particular saddle. And another question, now that we know that saddles don't have to be complex flat connections, a non-trivial question is, can this alpha star, which dominates this behavior and dominates the behavior of coefficients, can it be not the complex flat connection, but one of the black swans that I was describing before? So that's interesting. And another interesting thing, but this is slightly more technical, is that Chern-Simons, even if it's a complex flat connection, is defined modulo 1. But here there is an actual number. So the C effective is a very particular integral lift of the complex flat connection or this black swan phenomenon. So there is an integer here in the game, and question is, what is this integer? So this should be an interesting invariant of a three-manifold, and again, we don't have an intrinsic definition without reference to Stokes coefficients. So I phrase this collection of questions as something that I hope to see done in the next year or so. And again, thank you for your attention. I have to admit, I'm not an expert on Rademacher sums. I learned it to the extent that I can plow through one manifold at a time, and it takes me roughly a week to complete it, of course, with life destructions and other things. In every case where it has been verified, which I think is a very small number, it agrees. So that's a good news. But I'm not, I mean, I encourage others, thanks to your question, who know it better or more comfortable to try to see if it agrees in more frequently or another key. That's yeah, absolutely, and that's exactly my hope or interest perfectly aligns with your question, and that's the reason why I was not happy or I mean content with an answer that, oh, these are just something that we add by compactification divisor. So that's why I intentionally gave that answer, encouraging people to think about, because I feel that there should, I mean, there should be much better answer to this question, and I don't know. Yes, yeah. So I didn't give you explicit examples, but yeah, for again, we expect for past 30 years they should be, but in simple manifolds we have never seen them for, I don't know, 25 out of these 30 years. And more recently, in particular, in this recent work with Pavel, we actually now see many black swans, but again, they occur not in the simple instance. If you do a surgery on any twist knot, something we studied in the paper with Gerald in the video, they never appear. Any surgery on any twist knot, we don't see them, but maybe there can be even there, but nobody has seen them so far. But if you connect some of two twist knots and do surgery, then they appear. So in other words, you have to go like extra mile. So that it's precisely perfect instance where of using this analogy with black swans, because in simple cases they don't show up unless we explore Australia, and then once we go to further territory, then we start seeing them. The answer is yes. So that's right. So that's why now I would say picture is qualitatively clear and supporting the fact that yes, perturbative complex transassignments requires non-perturbative completion, which is beyond just complex trans. That would be at least my take. No. Yeah, so that's, yeah, thank you for the question. I would say some aspects of it persist. For example, asymmetry always seems to be there in all contexts. But false and mock are very baby cases, which are, again, I used for like test cases or something simple to be concrete. But I think nothing from false and mock is crucial to all these vast generalizations that they suggest. Yeah, so in particular, that was the goal of this tool, that it relies in no, I mean, I know here the interest is resurgence and modularity, but so I don't want to offend modularity part of community, but our goal was to produce a tool which does not rely on modularity. So therefore, now if you want to connect it to modularity, you can. There is a tool, but also if you have a Q-series, so I come from more like quantum topology. So to me, there could be Q-series which has nothing to do with modularity. Not even that had something else, for instance, the tool can still be used. So that's what makes me personally happy. Yeah, so as we were discussing, it's a criterion, and one has to be cautious, because when you see something that's not an obvious saddle, it could be renormal, which I think it's still interesting. It's like a cousin of black swan. It's something unusual, something you don't expect. But it could be also phenomena where criterion is a little blind to, and you know that it requires non-perturbative completion. So it's a good question. I think it still belongs to the same discussion we had earlier, but all I can say is we need to, collectively, we need to explore it more. No, in the Borel plane, it's a finite distance. So that's the point. So it looks like a normal singularity, like one of the Chern-Simons values should be there. It's not. That's a good question. No, we haven't looked at it, but I think we should, or you should. One should. That's a very good question.